Bryce, do you wanna try to share a screen?
Sure. Okay, you can see this, I guess.
Yes, that's great. Hi everyone, welcome to our Wednesday seminar. Today we are very happy to have Bryce Cyr from McGill University, and he's going to tell us about his work on supermassive black holes from cosmic strings.
Thanks. I'm very impressed you got my last name right as well. Most people really butcher Cyr.
I searched that actually.
Yeah. I'm very impressed. Yeah, I'm burdened with half of an English name and half of a French name. In Canada, that's a big no-no, I think. But anyway, thanks for the invitation. I really appreciate it. It's great to be able to talk about what I think has been an exciting project with my supervisor, Robert, as well as one of the other graduate students in our group, goes by Jiao Hao, who I think is just starting her PhD this upcoming fall. So hopefully you can look out for more interesting things from her. So yeah, the title of my talk is Direct Collapsed Black Holes from Superconducting Cosmic Strings. These are two things that I guess probably haven't been seen together before, although of course cosmic strings and superconducting cosmic strings have such a wide range of interesting phenomenology that it was bound to happen eventually. Yeah, so just before I start, I guess if anybody has any questions, I'm not sure how the format is here, but I'm happy to be interrupted at any point to clarify or to just talk about stuff. Yeah. So first, I'll talk a little bit about some of our motivation, which is what I would call the mystery of high redshift quasars. I'll discuss a little bit of the observations that have been made very briefly, certainly not an expert on that field. I'll discuss how people think they can be formed, because that's the mystery, I suppose, is we don't really know the right way to form these things. And I'll discuss what are going to be kind of the main point of the talk, which are these direct collapse conditions, which I don't want to spoil yet, but I'll get there in like 5 or 10 minutes. From there, I'll do a brief overview of some topological defect stuff. I think probably it's not super necessary in a group that is probably very well versed in these things, but just for the coherence of the talk, I'll talk a little bit about different types of defects very briefly, and specifically discuss photon production from a cosmic string loop, because that will be important for what follows, which will be kind of the meat of our paper, which is applying these direct collapse conditions to halos that are seeded by superconducting cosmic strings. There are going to be some great constraints that we can write on the parameter space of superconducting cosmic strings by considering not just these direct collapse conditions, but also the radiation pressure that can kind of inhibit some collapse of structure in one of these halos. I'll discuss a little bit of predictions, although I have to say that this is kind of venturing into like the current work category, because there are a lot of nuances that will go between applying constraints that already exist in the literature to our specific model, as will become clear. And then after that, I'll just do a brief summary and conclude. Yeah, so to begin, high redshift quasars are really interesting objects that people have been observing for a decade and a half, maybe a little bit longer. I mean, quasars in general are things that people have seen millions of. They're not super interesting anymore from an astrophysical perspective, but these high redshift objects are really interesting. So here I'm showing a plot of, I guess, most of the known high redshift quasars. There's about 200, maybe a little bit less. And you can see that these objects extend to super high redshifts, at least by astrophysical standards, all the way up to 7.5 and above. And what makes these things so interesting is that to see a signal from such a far redshift, you have to be producing a lot of light. And so the main excitement around these quasars is that the central engines in these quasars, the active galactic nuclei, which is essentially a fancy way of saying you have a supermassive black hole in the center that's accreting a lot of matter, that's emitting a lot of photons, and it's also spewing out these massive jets that are obviously extremely powerful if we're going to observe them all the way down at our lonely redshift of 0. So just by looking at the spectra and the luminosity of the quasars, astronomers can give a mass estimate on these central engines, and they're huge. They're about 10 to the 9 solar masses. And at redshifts of 6.3 to 7.6, that massive of an object is very difficult to explain. And I guess I should say very recently, a couple of months ago, there was a paper talking about 2 other potential quasars that have been detected. Now, I think, at least for astrophysicists, this is still a bit controversial. There's a lot of things that need to be checked and double checked before they claim this is a detection, but just to get people a little bit excited, that they may be reporting a detection of some 10 to the 8 solar mass black holes at absurdly high redshifts of 13. So the papers are just below if you want to take a look at that. So that could be very interesting, or it could be nothing. You don't know at this point. So how do we form these things?
Can I just ask you, what's the redshift at which reionization is supposed to take place?
Yeah, so I guess cosmic dawn, when the very first stars are turning on, happens roughly around a redshift of 20. But full reionization is expected, I think, from Planck. They can kind of put bounds on it of being between redshift of like 7 and 10 or 11. So it's right around the same time, yeah.
Okay.
Yeah. Okay, so how do we form these things? So obviously the most conservative thing we can do is say, well, let's just take standard lambda CDM and see what type of black holes we can get through typical accretion channels. So if you do this and you say, okay, maybe in a very optimistic scenario, my first population 3 stars are forming potentially at a redshift of 20 or 30, let's just say 30 for the purposes of this example. They typically have masses of about 100 solar masses. And so if they die and they collapse and they turn into black holes of similar mass, how heavy will they get by a redshift of 6, for example? So you can see here, there's, I guess, spoilers because I didn't split the slide up very well. But if you assume a maximal accretion rate, which would be the Eddington rate, which is found by just balancing the radiation pressure of the accreted matter with the gravitational force of the black hole. For typical values that astronomers use of this epsilon parameter, just taking the time between a redshift of 30 and a redshift of 6, you can see that you're only growing these things to about 10 to the 7 solar masses. So if you have this maximal growth the entire time, you're still a couple of orders of magnitude short at a redshift of 6. But not only that, Eddington accretion, as I said, if it's the maximal growth rate that a black hole can have, is very difficult to maintain that for a long period of time. There's all kinds of feedback that these early galaxies undergo that have been simulated before, that essentially say that it's even difficult to keep growing at this Eddington rate continuously for a long time. So really what you would need is some sort of super or hyper Eddington accretion rate, which breaks this Eddington limit. And this is something that can happen, and I'll discuss a little bit about that later. But if you want to invoke that, you kind of need a good reason for it. And I don't think that people would expect that the standard seeds, the standard population 3 black holes would be able to undergo that. So in order to kind of get around this problem, people have said, well, what if we can form black holes that have a mass of 10 to the 4, 10 to the 5 solar masses immediately? If you can do this, of course, you don't have to wait so long to get up to 10 to the 9 solar masses, even if you just grow at the Eddington rate or slower. So this is a tempting idea, but the question really remains, how would you do that? How would you form a black hole like this? And in the literature, it seems like there's 2 ways that people have considered. If you have some very dense environments, say you had some early star-forming galaxy that created a whole bunch of population 3 stars, really clumped together at the center of that galaxy, then as each of them die, you can have subsequent mergers, these runaway merger processes that take place. And in some models, you can find that you can get these initially heavy black holes of 10 to the 4 solar masses through these processes. So that's one way. And another way that has been considered maybe in a little bit more detail, as far as I've seen, is what is called the monolithic collapse of a metal-free gas cloud. So in typical Jeans theory, what happens is you have a cloud of primordial gas, and as it starts to collapse, it fragments, and each of those fragmented patches turn into stars on their own. That's the normal star formation picture. But if you were able to, say, come up with a set of constraints or conditions that would allow your gas cloud to collapse without any fragmentation, then you could potentially form essentially one supermassive star in the center that takes all of the gas from the gas cloud and collapses into a heavy black hole at early times. So this is the idea that we're going to discuss in the context of cosmic strings. But first, before we do that, we should discuss which type of conditions are necessary to collapse a gas cloud without any of this fragmentation. So these will be the direct collapse conditions that I'll describe. And I'm mostly taking this from this reference here, Iniyoshi, Visible, and Heyman, which is a really great review on formation of massive black holes in the earlier universe. I mean, not early universe, but from astrophysical standards. And so, as I said before, the idea is you want to collapse a black hole. You want to collapse a primordial gas cloud without fragmentation. And if you do this, many of the simulations that have been done by these authors and others who are all well cited in this review show that this initial overdensity at the center will grow at a super Eddington rate and collapse at a black hole once it reaches a mass of about 10 to the 5 solar masses. And this is generally because these supermassive stars that you form have an interesting density profile, but one that is such that most of this mass is piled in towards the center, and then it just hits this gravitational instability regime where essentially the Hooke conjecture is satisfied and you have too much mass crammed into too small of an area and it collapses. At least this is what the simulations say. So I'll write down here a set of 3 of these direct collapse conditions that I'll say. Yeah, sure.
I thought on the previous slide you were assuming a black hole. No?
So here we're trying to discuss how you can get a black hole.
Oh, how do you get the initial black hole?
Yeah, exactly. So how do you go from something to a black hole?
Okay.
Yeah. Thanks for the question. Yeah, so I'll formulate these 3 conditions, and if they're all satisfied, then one would say that this direct collapse scenario, where your primordial gas cloud essentially turns into this black hole, will likely happen. So the first condition is very simple. You need to be able to grow your star to 10 to the 5 solar masses in order to reach this instability. And so you must have at least 10 to the 5 solar masses of baryonic matter. So I'll write this condition as the boxed equation here, but really it's just saying if you have some halo with baryons inside of it and the bound baryon mass is 10 to the 5 solar masses or higher, then we can collapse, or at least we have enough mass to be able to satisfy this first condition. So the second one is tied more to the accretion rate. So again, these simulations show that the accretion rate is really an important quantity when determining whether your gas cloud is going to fragment or not. And they find that high accretion rates are absolutely necessary in order to prevent this fragmentation. So if you have the collapse of some gas cloud at a Jeans mass, then the typical accretion timescale, the typical accretion rate is set by really just the Jeans mass over TFF, which is the free fall timescale. And that's the average time that it takes for a shell of mass M at a distance r from the center of a protogalaxy, let's say, to fall to the center of that overdensity. So if you just plug in the equation for the Jeans mass and for the free fall time, you can find this relation to the temperature of the baryons in your halo. So this is essentially the virial temperature of this protogalaxy. And it's been found that you need this temperature of about 8,000 Kelvin or higher, both to accrete at a fast enough rate to avoid fragmentation, but also to trigger the collapse in the first place, because a temperature of 8,000 Kelvin is when a halo, a baryonic halo, transitioned into what's called an atomic cooling halo. So typically halos are characterized by the cooling processes that keep the gas cold. Usually this is, if there are other metals in the gas, it will keep the gas cold. If there's molecular hydrogen in the gas, then collisional excitations within the molecular hydrogen will allow for radiative cooling of the gas. And that'll be essentially the next condition. But if you get up to a temperature of 8,000 Kelvin, then the cooling, sorry.
Can I interrupt once more?
No
Because
problem.
I'm trying, I'll keep it lively this way. The temperature comes in to the Jeans mass or Jeans mass?
Yes, it comes in through the Jeans mass because it's related to the sound speed in the
I see.
yeah. So it comes in through the sound speed in the Jeans mass, and then the sound speed is related to the temperature of the baryons.
Right.
Yep. Okay. Right. So if you hit 8,000 kelvins, then your halo starts to cool through atomic line transitions, and that essentially triggers the collapse. So what, in simplified terms, this will require of us is to have a virial temperature in our halo that reaches 8,000 Kelvin and sticks around 8,000 Kelvin for the collapse itself. And then finally, the third condition is that if we want to get our halo to such high temperatures, we have to suppress these other cooling pathways. So as I mentioned before, if you have metals in the gas, metals in the baryonic matter that's in your halo, then this will cool the gas. And so one thing that we require, and is required of all of these scenarios, is that you have no prior star formation, because if you form stars beforehand, then this is just going to be polluting your halo. So you really need this overdensity of pristine, i.e. only hydrogen matter. And on top of that, as I said, even if you just have hydrogen, hydrogen itself can cool the gas by forming molecular hydrogen, and collisional excitations, again, start to cool you prematurely. So in order to dissociate the molecular hydrogen in a halo, you need what's known as a Lyman-Werner background. So this is really just a flux density of photons in this energy range here, just below the hydrogen, I guess, energy levels. And if you have a strong enough flux, so a flux density greater than some critical flux density, then essentially as soon as you form a molecular hydrogen, it's dissociated by this background. And so people have looked at the critical flux that you need in some optically thick medium in the context of these direct collapse black holes. And so I've just quoted the values that you need in this flux here in astronomer units, and then here in the units that I'll use for the rest of the talk, which is natural units. So these are the three main conditions that one needs to satisfy. And there's a great little flowchart that they present in their paper, which, I mean, we can follow along and see what happens in a particular area. So if you have a collapsing protogalaxy and your temperature is above 10 to the 4 kelvins with no star formation, then you get this pristine gas. So this is just hydrogen waiting to collapse. If you allow for H2 cooling, so you don't have a Lyman-Werner background, then you essentially just form galaxies, which is not what we're looking to do here. If you do have some Lyman-Werner background that's greater than the critical value, then there's no H2 cooling. And so your pristine gas collapses into this initial protostar, which, as I mentioned before, grows at this extremely fast rate of about 0.1 solar masses per year. And it grows and it grows and it grows until it reaches 10 to the 5 solar masses, at which point it hits this GR instability and collapses into a black hole. Now, alternatively, if you followed this pathway, say you didn't have a hot enough halo, you would just form initially these population 3 black holes. And if nothing happens to them, then they just stay at 100 solar masses. But if one of them can find itself in a pristine gas cloud somehow, then it is also able to grow at this hyper-Eddington rate. So you don't need this intermediate step, but in order to get a black hole in a pristine gas cloud in the first place is also a little bit convoluted. So the most clean way to do this is really to follow, this trajectory here, which is what we'll look at now. Okay, so a big question is, are we able to satisfy these direct collapse constraints in the context of lambda CDM? do we need anything extra in order to do this? And the answer is it's very difficult in lambda CDM. So of course, if you are just looking to satisfy that first constraint, having enough baryonic mass, that's simple. You just wait and wait and wait, and you'll grow easily to a baryonic mass of much greater than 10 to the 5 in no problem with just Gaussian initial fluctuations. But it's the sourcing of this Lyman-Werner background and essentially the ability to keep the gas hot that's really difficult to do in standard situations. Because as I mentioned before, if you have a pristine gas cloud, it's just hydrogen. There's not really any way to source photons within that gas cloud. So you're not getting the Lyman-Werner background. It's possible that the first stars that exist in a galaxy, they of course have a lot of radiative photons that come off of them, and it does source a strong Lyman-Werner background. However, if you require this Lyman-Werner background to come from star formation in your galaxy, then you've ruined the other condition of not wanting to pollute your galaxy with metals. So it's kind of like you can't satisfy both of these at the same time. And within the standard lambda CDM picture, people still, of course, try and satisfy these constraints. And the way they tend to do it is by putting two galaxies close by to each other. One of them that's undergoing star formation and one of them that's not. And the star formation galaxy essentially just irradiates the other nearby galaxy with Lyman-Werner photons coming from itself. But again, this is a very fine-tuned process. How often are you going to get two galaxies that are close enough together to irradiate one another, while at the same time being at different stages and the perfect type of different stages in their stellar evolution? It's difficult to say the least. So if you could find a way to source essentially this Lyman-Werner background without requiring star formation, then that would be a very ideal environment to have these direct collapse conditions satisfied. So this is essentially where superconducting cosmic strings come in. They can save the day in the sense that if you have one of these loops that's residing, say, in the center of a protogalaxy, not only does it help grow the accretion of matter at early times because it possesses a gravitational overdensity, but it also is able to produce a large amount of photons in a pretty wide spectrum. And in particular, you can produce photons in this Lyman-Werner spectrum, part of the spectrum which will keep the molecular hydrogen at bay and potentially allow you to form direct collapse objects much easier. So on the right here, I've just shown a picture again coming from the review where they discuss the different growth histories of protostars at different accretion rates. So you can see that at a low accretion rate, you really start to grow a little bit. You get to be 10 to the 2, maybe 10 to the 3 solar masses. This is a population 3 star, and then it stops because of essentially feedback in the halo. But if you have a fast enough accretion rate, what ends up happening is you kind of just keep on piling matter into this very dense core, and there's not a limiting mass that you get to. So you keep on going until you hit this GR instability as it continues to go up here and collapse into a black hole. So this is just the results of simulations of these folks. Okay, so this is the initial direct collapse motivation. Now I'll talk a little bit about topological defects, but of course, if there are any questions, I mean, any time is good, but now is also good. Okay, so topological defects. I mean, I don't know if I'm the one who should be giving this lecture here in the context of people who are very well versed in this, but they form when the universe undergoes phase transitions. If you break local or global symmetries, you have a possibility of forming defects. And the type of defect that is formed is really determined by the topology of the vacuum manifold, hence why it's a topological defect. So in this picture I've drawn on the right here, I mean, your vacuum manifold goes from just this single point at the origin to being a circle. So in this particular context, you would form a cosmic string, but the different shapes of your degenerate vacuum manifolds can give rise to different types of defects. And typically, these objects are cosmologically long-lived because they possess some type of a topological charge, usually called the winding number, and that protects it from rapid decays, although there are still decay channels for these defects. That's what causes a lot of interesting phenomenology. But it goes without saying that if one was to be able to detect a defect, it would not only provide like amazing information about what our universe is like today, but it is able to give us information at the scale at which the symmetry is broken. So you're getting a glimpse essentially into the universe before a particular phase was broken. So you get all kinds of incredible high energy physics knowledge, including a window into the higher symmetry groups that may govern, gut scale theories, or somewhere in between gut scale and SU3 cross SU2 cross U1. So there's clearly a huge motivation to study these things. So in 3 spatial dimensions, you can get essentially 3 types of stable defects, and then people also talk about these cosmic textures. So if you have disconnected degenerate vacua, like I've drawn here, then in some regions of the universe, the field will fall in one side, and in other regions of the universe, it'll fall on the other side. Usually this is discussed in the context of the Kibble mechanism. So on scales that are larger than essentially the causal horizon at a certain point in time, your field is not correlated. And so it really is just random which side it falls into. And then as the universe continues to expand and these patches meet each other, as the field needs to interpolate from one spot in the universe to another, it has to overcome these potential barriers, giving you the domain walls in this particular case. So if you have a circle as your vacuum manifold, as I mentioned before, you get cosmic strings. And if it's S2, then you get monopoles. So if it's S3, for example, you get these cosmic textures, which I guess I would consider more to be just like regions of gradient energy that aren't topologically stable. So usually when a cosmic texture enters our Hubble patch, it begins to unwind and can release a lot of energy as well. People have considered cosmic textures in the case of like CMB spectral distortions, potentially the cold spot on the CMB, although I don't think that that's a viable solution anymore. But people have talked about these before, and they're also interesting. They're just not cosmologically stable. Right, so the Kibble mechanism really is just saying that your field is not correlated on scales larger than essentially the Hubble radius at the time of formation. But if you break a symmetry breaking pattern, then a few of your defects must form per Hubble volume. So if you're able to form topological defects, then you will form them, which is great because that's a universal statement for a particular symmetry breaking pattern. Okay, so in the context of our work here, superconducting cosmic strings can kind of be viewed as this type of asymmetry breaking. And so here I've kind of just tried to do a mapping between physical space and field space. So if you imagine that this is just some discretized slice of physical space, then we can say that, oh, maybe the field fell in the upwards direction here, right here, down here, and left here. And of course, we want this field to smoothly interpolate between all potential field values. So if you go around the circle, of course, you want to wind around in field space, which is what you do in this case. But what happens if you want to go, straight over the top of this hill? Well, that's exactly what the field does. Phi starts living not on the vacuum manifold anymore, but it climbs up this potential hill and sits again at the top. So the cosmic string is really just this region of trapped energy density at the top of the potential hill here. And if I now just extend this to 3 dimensions and I glue a lot of these slabs together, then you can see that the string itself just pierces all of these slabs, and a cosmic string is born, essentially. So the cores of these things, since it's trapped in this like old higher symmetric state, consists of all of the gauge and scalar particles that would have existed in this unbroken phase. It's also possible to break U1 electromagnetism in the core, which essentially makes the string itself superconducting. You can have bosonic or fermionic charge carriers that run along the string itself, which carry a current I. And so in these superconducting string theories, G mu, which is the string tension itself, and is related to the scale eta of symmetry breaking, and the current are really the only free parameters that you have. So if you pick a spot on this G mu versus I parameter space, then you've essentially defined all of the possible phenomenology that you can get out of such an object, which is another reason why they're interesting to work with, because there's not a whole lot of knobs that we can tune, which is nice. So as I said before, with the Kibble mechanism, you expect there to be a few of these long strings per Hubble volume. And in general, the self-intersections and collisions with other long strings can form this distribution of loops, as I've crudely drawn here. And these loops have radii that tend to go between cutoff radius given by the essentially by the energy loss mechanisms. In this case, I think usually it comes from cusp annihilations on cosmic string loops, emitting either a large amount of gravitational waves or a large amount of electromagnetic waves, depending on the value of the current. I've given these values down here. And you have loops from that small size all the way up to loops that can be some fraction of the Hubble radius at a particular time. So usually people give usually people write some of these parameter values like this. So alpha is generally 0.1. So usually your loops are not being formed with more than, say, 10% the size of the Hubble radius. Kappa and gamma are related to just the efficiency of electromagnetic and gravitational wave production on each of these cusp annihilations. And then beta parameterizes the circular nature of a loop. So the length of a loop is equal to beta times r. And if beta is 2 pi, then your loop is perfectly circular. We'll just take beta to be 10 to account for little variations that could take place. So there are some bounds, of course, that can come on G mu from CMB anisotropies. This one's been fairly robust for a long time. You can set G mu being has to be at most 10 to the negative 7, which is a nice dimensionless quantity. Pulsar timing arrays have been constraining stochastic backgrounds of gravitational waves for a long time now, and set a constraint, at least with the, the 11-year data set, I believe, of G mu being less than 10 to the negative 11, provided you have this distribution of this scaling distribution of loops. But since, like a year ago when Nanograv announced possibly detecting a signal of some common spectrum process, we're really unsure about what this bound should be. I know there's been papers by people in the field who have interpreted this signal as potentially being part of the stochastic background of gravitational waves from cosmic strings. And I believe that the value of G mu necessary to somewhat reproduce the Nanograv results is about 10 to the negative 10, between 10 to the negative 10 and 10 to the negative 11. So I would say this bound is not so robust these days, but we'll see what happens in the coming years. Okay, so how are photons produced from strings? Above, I've written just an effective action. I'm not going to really refer to it much after this, of just a Nambu-Goto string that has charge carriers that, of course, interact with the photon through this particular coupling. And if you just take effective action like this, then you can look at the photon production coming from different microphysics on the string loop itself. So there's cusp annihilations, and there's kinks. So I'll talk about cusp annihilations in a little bit of detail. So I won't talk about it right this exact second. There's kinks, which are essentially discontinuities, or almost like 90-degree like bumps on a cosmic string itself. And these kinks can collide and also produce photons. And then there's this gravitational Aharonov-Bohm effect, which is quite interesting, but is mostly just related to the fact that the cosmic string cusps and kinks themselves produce a departure from Minkowski metrics, and that can be interpreted as essentially a way to connect gravitational effects to photons. So this is an interesting effect, but it's quite weak. Usually scales as, I think, G mu squared. So it doesn't actually produce a sizable amount of photons in most cases, I would say. So if we focus on cusp annihilations, the important things to remember are that these strings have intrinsic windings. I've indicated some winding here. And anti-strings are really just cosmic strings with the opposite winding. So if you form a cusp, as I've kind of drawn over here, so your string loops are constantly oscillating. They have a period that's about equal to their radius. And about once per oscillation time, if you look at the equations of motion coming from the Nambu-Goto action, you find that there are these essentially naively luminal points that the string itself, I guess, creates. And it doubles back on itself in a sense. So you really get this cuspy shape that forms once per oscillation time on a cosmic string loop. And if you're just to run these windings backwards, you can see that in the region where there's this overlap, it really does look like you have a string and an anti-string. One part of the cusp is wound in one direction, and the part that it's in contact with is wound in the other direction. So this looks locally like string anti-string, and it annihilates into particles. So the string really just smooths itself out by emitting a burst of gauge and scalar fields. In the context of superconducting cosmic strings, you get a big boost to the photons that you produce off of a cusp annihilation. And you can find that the power per unit frequency is given here. So this is, I guess, work that was done, I think, at Arizona as well, like 10 years ago. And the photons that you produce come in some solid angle given by this, which is very, very narrow. So in fact, this picture is terrible because it looks like these particles are being spread over some wide direction. But in fact, the solid angle is tiny. And so this is a highly beamed process. You produce a whole bunch of photons in a very specific direction. Right, so that's, yeah, so that's, I guess, what I wanted to say about cusp annihilations, and this will be our primary way to discuss sourcing a Lyman-Werner background in the context of these direct collapse conditions. Right, so now I'll move on just to the conditions themselves and how we can apply them to superconducting strings.
So you also have to assume some magnetic field that will produce these currents?
Yeah, I mean, that's a great question, and it's a topic of some work that we're doing right now. For the purposes of what I'll present today, I think it's suffice to just assume some constant current on a loop with a radius r. Most of the parameter space constraints are just given in this flat G mu I plane, where you make some assumptions about the current, and you don't discuss too much about the generation mechanism. Although it turns out that this mechanism is going to be incredibly important for our work, and it's stuff that we're still looking into. So,
okay, thanks.
Yeah. Okay, so how does a cosmic string accrete matter? So this is taken from work of another one of Robert's students 7 years ago, I guess now. And the idea is that you're just following the Zeldovich approximation of spherical mass shells that are decoupling from the Hubble flow and being attracted to this overdensity that is sourced by a cosmic string loop. So in this particular picture, I guess we can say that this R of X is the physical distance from the center of some string loop to a mass shell that you're wanting to collapse. So A of X is just the scale factor, of course, with X being some proxy for time. This Xi is the co-moving distance from the center of the loop. So A times Xi is really just the physical distance. And B of X is where the interesting physics comes up. This quantity parametrizes the difference in what would happen to this mass shell in the presence of a loop versus if a loop is not there. So B of X equaling 1 is essentially the statement that there is no other overdensity at the center of this object. So in order to understand how different mass shells turn around and accrete themselves onto this overdensity sourced by the cosmic string, you need to first note that the initial density fluctuation is just given by essentially the mass of the loop itself divided by the total mass of the halo that it is trying to attract to itself. And then by setting, I think they set r dot equals to 0, which corresponds to the turnaround radius. So the radius at which this mass shell stops expanding with the Hubble flow and starts to actually fall back in. And in the Zeldovich approximation, people a long time ago have worked out essentially the differential equation that governs the dynamics of this B term. And so this B, this difference between there being a loop there or any overdensity there, this is not necessarily just a loop, it could be a primordial black hole, it could be many things, is governed through this equation where your overdensity parameter is just here. And in the paper, this paper here, they solve this equation in the different cosmological epochs to essentially determine how a cosmic string seated over density grows with time. And as one would expect during radiation domination, things don't grow very much at all. The radiation pressure is very high in those moments, and so you just don't accrete a lot of matter at early times. But after matter radiation equality, this string seated over density of all of the mass shells falling onto and into the cosmic string loop center start to follow this inverse redshift relation, essentially. And this is something that's been known through different simulations and different work by Ostreicher and others in like 2006, I want to say, 2005, 2006, in the context of primordial black holes, has been known for a long time, this type of.
The fact that it's radiation or matter domination comes in this 3/2 or something, or where?
So the fact that it's radiation or matter domination, I don't think comes in this equation here. I believe that it, well, I'm trying to remember now. I mean, I guess the X itself is determining which region you're in, because X will have a different time parameterization, whether you're in radiation dominated or.
When you wrote A of X, did you mean to write X over there? On that previous.
Sorry, on this one. No, I believe it's A of X. I can double check the paper afterwards if you'd like.
X is A of T.
Yeah, A of okay. This is this is confusing. Okay, so X should be in radiation domination, I guess. T over T equality to the 1/2, and so A of T over T equality to the 1/2 is.
Are the two A's the same?
The two A's are the same. Yeah, this A is the same as this A.
Okay.
Okay. Yeah. I'm sorry. I know that's definitely a bit confusing. Yeah. Okay. So what is found essentially is this growth rate, and so one can say that essentially the influence of the loop itself is important for the initial mass shells that fall on, but after a little bit of time, the overdensity itself has already grown to a few times the size, the mass of the loop. So for example, at recombination, your nonlinear overdensity is 3 times roughly the initial loop mass. And so it becomes over time less and less sensitive to the fact that there's a cosmic string there at all, and continues to grow on its own without this. So once you start to form an overdensity in this way, it seemingly will continue to grow. But in our cases, it's important to keep the cosmic string loop around because we want the cusp annihilations to be able to source Lyman-Werner background, for example. Okay, so people have considered potential seeds of ultra-compact mini-halos and supermassive black holes using these types of expressions before. And I think that this was something that bothered me a little bit and made me want to take another look at this, is there seems to have been a bit of a hole in some of this literature in which some authors would propose seeds for supermassive black holes, and those seeds would be coming from cosmic strings, but there was never really any discussion about how you went from a cosmic string to a black hole. I mean, this is a non-trivial process, and essentially one of the main reasons that I wanted to investigate this a little bit further. Okay, so just heuristically, so we can kind of have a big picture understanding of what's happening. The loops that will satisfy direct collapse conditions generically form before matter radiation equality, but we ignore any of the accretion that takes place before that time because it's very negligible. At matter radiation equality, the dark matter starts to accrete onto this overdensity, and you start to form essentially a string-seated dark matter halo. But you're still in a tightly coupled plasma because recombination has not taken place yet. And so the gene's mass itself is really high. Usually people will discuss whether or not baryons fall into a halo based on whether your overdensity is greater than or less than the gene's mass. And in this case, we're much less than the gene's mass before recombination. So we don't have any baryons between T equality and recombination, but we do grow this dark matter halo. And after recombination, the baryons all of a sudden are not tightly coupled. The gene's mass drops quite drastically. And for particular loop radii, let's say, the nonlinear mass does exceed that of the gene's mass. And so you will start to accrete baryons, essentially right at recombination. These baryons fall in to the halo and virialize on this free fall timescale that I'll discuss in another moment. So this is the main picture of the infall, at least. Okay, so to satisfy the first condition, it's very simple. We have our accretion mechanism. The mass of baryons is really just related to the total nonlinear mass multiplied by this factor of the omega baryons over omega matter, which is roughly 1/6. And so if you require that your baryon content in this halo has to be at least 10 to the 5 solar masses, then you're automatically satisfying the other constraint, the one that your dark matter halo essentially is greater than the gene's mass, because the gene's mass is 10 to the 5. And so if you have 10 to the 5 baryons, in order to satisfy this condition, you have at least 10 to the 5 solar masses in dark matter. So this condition we don't really need to worry about. And so what we would like to present most of our constraints as are radii of string loops. So as I said before, there's this range of radii that when you form loops exist that go between the cutoff radius, whether from gravitational waves or from electromagnetic interactions, all the way up to essentially the Hubble size at the particular time you're looking at. And we want to ask the question, in a particular loop distribution, how many of these loops would be able to satisfy these conditions? So in order to do this, it's kind of easiest to phrase these constraints in terms of the minimum or maximum radii that you would need to satisfy each individual constraint. So in this case, you can write down critical radius to satisfy the enough mass constraint. And so any string loops with R greater than this critical mass will accrete enough matter at T equality or within one free fall time after T equality to feed this initial protostar and create the black hole. So there's this implicit assumption that this RCM is going to be bigger than the cutoff radius coming from the other processes, which is a good assumption. We've checked numerically. And so this essentially says that there's this range of string loops that could accrete enough matter. Now, this is not saying that this will create the black hole. There's other conditions that we have to satisfy, but this is just for the enough matter constraint. Okay, the second piece of the puzzle is the virialization of these baryons. So as I said, at recombination, the gene's mass drops and baryons start to fall in. As before, they fall in on these free fall timescales, which I guess is given in the bottom right here. And this is roughly a Hubble time. And so I guess what I say here is that the radius that a shell of matter beginning to collapse at some redshift Z would have in the absence of a loop is given by this nonlinear radius. So essentially the picture should be that you have your string loop, there's some shell of matter that's falling in, and after a free fall time, then this shell of matter has been virialized and sits at a virial radius, which is roughly 1/4 the nonlinear radius that you initially started at. And so as these shells start to fall in to the center of your overdensity, they undergo many of these things called shell crossings, which is the statement that as these shells, like a shell from inside this shell that I've written here, as they cross each other, the baryons interact with each other and they start to thermalize. And after many of these shell crossings take place on this free fall timescale, the initial overdensity, the baryonic overdensity at the center of this, this string-seated overdensity has a uniform temperature T virial and sits at this R virial radius. Okay, so to satisfy that second condition, which is that we wanted our virial temperature to be above 8,000 Kelvin, we can simply use the virial theorem to relate the mass inside of this overdensity to its temperature, which is a very straightforward exercise. And we can get this radius, this critical radius, to form an atomic cooling halo. So again, this is an upper bound, this is a lower bound on the radii of a string loop. And it turns out that this condition is degenerate with the enough mass condition. So if I just flash this one back for a second, these two conditions have the exact same scaling with G mu and the same prefactor. The only difference is the redshift dependence. And so you can show that this constraint actually doesn't become the dominant constraint until low redshifts. So generally speaking, we kind of ignore it. And we say that if you have enough mass to form this black hole, then you're automatically going to have a hot enough virial temperature and satisfy this atomic cooling constraint. Okay, the third condition was this Lyman-Werner background. And just borrowing the formula from before, the motivation that we have here is that as your matter is collapsing, it's producing this optically thick medium. So the radiation that's produced from these cusp annihilations on the superconducting string, while it's initially very beamed, undergoes a huge amount of scatters during a free fall time. And this huge amount of scattering essentially isotropizes the initially highly beamed radiation and produces this Lyman-Werner background. And so all of the photons that are produced from when the baryons start to fall in until they're properly virialized, which is roughly between redshifts of 1,000 and redshift of 500, get trapped in this halo and contribute to the Lyman-Werner background. So by just considering the photons in the Lyman-Werner band and requiring that the Lyman-Werner background is greater than the critical background that we mentioned before, you can get this a little bit messier constraint on the radius of a string loop that you would need in order to create a strong enough dissociating molecular hydrogen background. And this ends up being I'm always so bad at upper versus lower bounds. This is a lower bound. No, sorry. I'm sorry. I'm completely blanking on that one. Yeah. Okay. So this is a this ends up being an lower bound on the.
So this is the size of the loop that would give you enough Lyman-Werner background.
Yeah, exactly. And
Maybe
loops
larger loops.
Right. So loops smaller than this will produce stronger Lyman-Werner backgrounds. So this is an upper bound on the string loop radii.
I would have thought the opposite.
Yeah, I initially thought the opposite too, but I think it turns out that the smaller loops produce more of the Lyman-Werner radiation in the first place.
Maybe they're oscillating more rapidly.
Yeah, I think that's correct. Yeah, the oscillation time scale is much shorter, and so you produce more cusps in a free fall time scale, and therefore produce more Lyman-Werner photons. Okay, so this is the good part of having a superconducting cosmic string is you're able to satisfy this Lyman-Werner constraint. But the bad part is that, of course, when you have photons, you're also producing a photon pressure. And we really don't want to disturb the accretion dynamics. I mean, we don't want to have radiation pressure that's so strong that the matter that's trying to fall in is instead being pushed away. So it's important to also calculate the force of this radiation pressure. So what we do here is we compare the ratio of the radiation pressure, which I've given above, with the self-gravity of the gas cloud at a particular point in time. And if this ratio is greater than 1, so if Fg over Fp is greater than 1, then the radiation pressure is like negligibly small compared to the gravitational infall force. And so we don't worry about it so much. But as you can see here, this radiation pressure depends, is most dependent on the highest values of omega c, of the frequency of photons coming off of a cosmic string cusp. And so we need to set some cutoff frequency. The spectrum doesn't go on forever. And I guess it turns out that at this particular value of omega c times T equality, you are at the limit before electromagnetic back reaction plays an important role in the spectrum that would be coming off this cosmic string cusp. So this is kind of the upper bound on the frequencies coming off a string that most people consider. And so that's what we consider here. So you also get, so as before, we had an upper bound on the radius coming from the Lyman-Werner. We also get a lower bound coming from the radiation pressure on these string radii. So to turn to maybe the constraint plots that people are usually more interested in, this is, at least to my knowledge, one of the more recent like sets of constraints on G mu versus I for superconducting cosmic strings. There's lots of great constraints coming from CMB anisotropies, pulsar timing, spectral distortions, BBN, radio observations with the Park survey, 21 centimeter. It turns out that if you want to satisfy all of these constraints at the same time, you lie, unfortunately, deep within the already constrained regions. So many people would see this and say, oh, well, I mean, maybe it's time to pack it up and go home. It's not a very interesting region of parameter space. But there are quite a few nuances that I think are important to discuss, which is that these constraints are difficult to apply directly to our model. Because, you know, first of all, when people write up these constraints, generally speaking, they're not discussing the current generation on these loops in the first place. They're just saying, okay, all loops have the same uniform current I at all different radii. And this is maybe not the best assumption because we know that, as Tanmay said earlier, the current induced on these loops is proportional to your local electromagnetic fields. And so if you have variations on different length scales at different times, then this is a very simplified assumption in the G mu versus I parameter space. On top of that, these constraints, of course, assume that all loops are superconducting. I mean, this is what I would do. This is what anybody would do when writing up these types of constraints. But it is possible to find examples where not all of the loops carry currents. Sometimes you can have specific scenarios where the current on a loop is dissipated in some regions and not in other regions. You could have multiple phase transitions where some of the loops become superconducting and some don't. So that's another thing that we kind of need to think a little bit more carefully about. But I think the most important thing is that most of these constraints come from the smallest loops. And this is because of two reasons. One of them is that the smallest loops are the most abundant in the universe, so they have the most areas at which they could affect things. But on top of that, because of their faster oscillation periods, they're also producing cusps and kinks more often and creating much more interesting signals that we can be searching for. But the loops that satisfy these direct collapse constraints are generically going to be a lot larger in radii than the smallest loops in a network. In fact, you would never expect the smallest loops in the network to be able to source these black holes. And so one needs to kind of reevaluate these constraints in the context of like, what do they say about loops of larger radii in particular? So we're currently looking at reanalyzing some of these constraints to discuss in a future paper. So I would say that what we've done here is, you know, not stringently constrained yet, but it stands as a pretty good proof of concept that there is hope that in a lot of these idealized cases, we can form direct collapse black holes using superconducting cosmic strings. There are still some simplifications that we need to address. In particular, there's going to be relative velocities between the loop and even the dark matter and the baryons can additionally have different velocities. And right now we're working in a frame where everything's at rest. It's nice and simple. When you go to a more realistic scenario, accretion will become slightly more difficult and maybe a little bit less symmetric. And so this is something that we need to address in the future. Yeah, so I think I'm a little low on time. So just to say that our future work is kind of dedicated to coming up with a good prediction on a number density of superconducting strings that can form into black holes that can be observed and probed by observations of these high redshift quasars. So in order to get there, we have to understand how our prior constraints that I showed on the parameter space plots apply to us in our model. We need to include some of these more complicating effects like velocity dispersion. But after we know, at least on our end, what a good number density looks like, we can start to evolve this forward into the nonlinear regime. At redshifts of 30, when other galaxies are forming, you have a whole bunch of mergers that can take place and can further amplify the growth of these objects. And so we're hoping that by working with some numericists in the Netherlands, Pratika Dayal and Maxine Trebisch, we are hoping to make some good constraints on either superconducting strings or some predictions for future observations, depending on how rare these objects really are, because we don't have a good handle on that yet. So as a summary, this is kind of the picture as to what happens at different redshifts. And so maybe I'll just leave that up for questions at the end. But just as the final conclusion, there are 3 constraints that we applied from the direct collapse formalism to superconducting cosmic strings. There are regions that are presently constrained, but we will see what happens in our current analysis. And we'd like to make some great predictions or direct constraints in the future. So thanks a lot for listening.
Thank you. Thank you for the interesting talk. Any questions from the audience?
I don't want to be the only one asking. I was a little confused. I mean, you said that in the parameter space, the strings are ruled out. Is that what you said? Like this blue square is where we should be?
Yeah, I would say that at least naively, in order to satisfy all of these direct collapse conditions simultaneously, it looks like the G, mu, and I values have to be in this blue square.
So, and then you propose some ways out of this? Yeah.
Yeah. So I mostly was,
yeah.
I would say that the most important way out that we could potentially see is the fact that these constraints are generally coming from loops with radii much smaller than what we need for direct collapse.
I see.
So we need to see how these constraints evolve when looking at their contribution coming from larger radii and not just ones that are at the cutoff.
I see.
Yeah.
Now you don't really need a large loop, right? You can have many, like a cluster of small loops, and would that also work?
Yeah, so that's another thing that we've been kind of toying with, because not only can it produce a similar overdensity, but if you have a lot of small loops, you could potentially source your Lyman-Werner background even easier. Yeah, so that is something that we've also been thinking about. But I guess the question is, why would one expect a lot of these small loops to be clustered together? Because I think generally when we're thinking about populating a loop distribution, at least the way that I look at it is that I assume these things are roughly homogeneously distributed in space.
Yeah.
So how do I get, 5, 10, 20 small loops together without some other overdensity that attracts them in the first place?
Yeah.
But it's a great question, and yeah, it's a good idea too.
Difficult questions too.
I have a question.
Yeah.
Excuse me. Assuming a non-homogeneous background with the loops, what happens if, say, a loop encounters a black hole that's already been formed?
Right. I mean, that's a good question. I would say that if the black hole has already been formed at these extremely high redshifts, then it's got to be a primordial black hole. So in terms of the interactions, I don't think that there would be any interactions aside from, gravitational interaction. But you could potentially still form a direct collapse object around the cosmic string loop, which would then afterwards merge with this other black hole and would give you a boost in the mass of your object at the end of the day. But I don't know if there would be much like direct interaction between the two of them that wouldn't already be gravitational and things that people have considered in the past.
Okay, thank you.
No, thanks.
Any other questions?
There was one more question.
Yeah.
So these, you needed photons of about 10 to 13 eV.
Yeah, that's right.
These cusps, would they produce enough of those photons? I mean, they produce mostly radio. So,
Yeah, I mean, at least that was the crux of the Lyman-Werner computation.
yeah, okay. So
yeah.
you use some spectrum.
Yeah. So I think essentially what we did was we integrated this over the Lyman-Werner range.
Yeah, the omega to the minus 2.
Yeah. And then we multiplied the power by the free fall time as well, because I think that's, we're saying that all photons produced during this free fall are being trapped in the overdensity. So yeah, I mean, this is the result of that computation. So there is a region, a non-zero region of loop radii that will produce enough Lyman-Werner photons.
Oh, okay, very good.
So that's definitely a nice surprise, and I think that's the hardest thing to realize in standard astrophysics. So if there's an alternative explanation for it, it could be very helpful on many levels.
Oh, very good.
Can I take a look at the last slide where you show the whole process?
Yeah, sure.
So in the end, the loop is still there.
Yeah, so I guess on the very far right-hand picture, the loop doesn't have to be there anymore. It really just has to be there during the collapse of the overdensity in order to continue to feed this Lyman-Werner background. So one could potentially say that, well, if my loop decays at, around a redshift of 300 or 400, then I don't care. It doesn't matter anymore. It served its purpose. But in order to keep the Lyman-Werner background, you need it here. Although I would say that in the absence of the loop, as I mentioned earlier, the dark matter halo will grow by itself. And so if you have the loop initially, say between T equality and T recombination, and then the loop dies here, then this baryonic overdensity is still going to form, but instead, I guess you're going to fragment and create smaller stars, and you're not going to form this black hole, for example.
I see.
So this is a process that has been constrained in the past when people have looked at early reionization. And I think that the conclusion was something like for G mu less than 10 to the negative 8 or 10 to the negative 7, that you were still safe from these early reionization constraints. But
I see. Another question is, so here in the end, the black hole should be spinless, right? Because you assumes
yeah,
spherical.
I guess, yeah. If it's a spherical collapse, it should be spinless.
Okay.
Yeah.
Okay. Thank you.
Problem.
Any other questions? If no, let's thank Bryce again.
Thank
Yeah,
you,
thanks a lot.
Bryce.
Thank
Thanks
you.
for the invitation.
And nice to meet you. Nice to see you.
Yeah, yeah, you too. I mean, I've
Yeah.
obviously read lots of papers, but never had the opportunity to chat. Yeah.
All right. See you
Yeah,
then.
see you.
Yeah. Thanks a lot. Have a great day.